Sure, you can just send me the recording.
Yep, I can send you this recording.
Okay, then I won't record.
Okay, hello everybody. Welcome back. Today we have some special things for you. So my friend Chong Min is here to teach us deep learning. And before we start, I'd like to give a short introduction to the new people that we have today. So Chong Min is my friend from Navy. He's now doing a PhD in the field of artificial intelligence at NUS. And I will let him introduce himself. But before that, I have two new people today. One is Chong Min's friend, who's called Chi Wong. I'm sorry, Kai Chi. Yeah.
Yes.
And another is actually my brother. So I invited him because
Oh.
he's learning to do ML and deep learning. So he's Ikin. Usually I will ask that people introduce themselves, the new members, but I think let's get started today first with the deep learning, and then next week if people continue to come, then we'll invite the new people to introduce themselves. The rest of the people here are regular members. They have finished 15 or 16 weeks with me doing the traditional machine learning. And last week we've finished the summary of it by doing a practice session from using Titanic dataset. So it is good to have the traditional deep learning, traditional machine learning fundamentals. However, the ideas that come with deep learning are a bit more different than the traditional learning models. And so don't worry if you didn't catch up on everything that we did on the machine learning fundamentals. So without further ado, I would like to invite Chong Min to present his background and also present his slides.
Okay, hello everyone. Can you all see my slides, by the way? Okay, all good. So I'd like to thank again Ikin for inviting me here. And I think this is going to be something interesting because we are going to touch on what is the hot trend right now on deep learning. Okay, but of course we are not going to go so far into the most current research because a lot of background is required for that. Okay, so I hope to be able to provide you the background here over 4 sessions. Okay, later I'll tell you roughly what will be covered over each session. And hopefully at the end of it, you are able to do very simple deep learning architectures yourself. You can go impress your friends. No, it's actually pretty simple. Okay, and the main thing that you require is perhaps a GPU, which is a graphical processing unit. Okay, because a lot of the operations are done over there for faster speed ups. Okay, so without further ado, let me introduce myself first. So who am I? I actually was a former Navy officer, and I left Navy about 3 years back. I went to do research in deep learning, and it's because I found that actually AI is becoming a very booming field, and I like to get involved in it. So I made a career switch. Okay, so now I'm a year 3 PhD student. I'm mainly do research on neural network architecture at the beginning. I did a paper on how to prune neural networks efficiently so that you can prune away most of the parameters and it can still run. So that paper was called DropNet, published in ICML. Right now, I'm doing more research on how to improve reinforcement learning methods like AlphaZero. Okay, AlphaZero is the program. The next version of the program that won Licedo. The program that won Licedo and Go is called AlphaGo. AlphaZero is the one that's trained from scratch. Okay, so I'm doing more of that kind of research now. If you're interested, you can feel free to ask me more about that. Okay, I mean, I could even talk about this, but this is a bit more advanced. Okay, this requires a few sessions. Okay, just to touch on AlphaZero itself will require about 2 sessions. Okay, so yeah, I also do some streaming for programming, for game creation. So yeah, feel free to go to my Twitch channel if you are interested. Okay, so that's it. Yeah, any questions for me? Okay, if not, I will just continue. Okay, just feel free to type in the chat. Just keep this session informal. Okay, so for the overall program that I have crafted for you is basically week 1, I'll do a rough overview of what's out there in the in the machine learning world, and I'm mainly focused on multi-layer perceptron. Okay, next week will still be on multi-layer perceptron, but the focus will be more on how to implement it on TensorFlow, one of the deep learning architectures. So I will touch more on what is TensorFlow, how to use TensorFlow. So that will be like the front part. Then we'll do some coding after that. Okay, I already shared the notebooks. Okay, I already shared the notebooks with you all, so you can take a look, even next week's notebook as well. Okay.
Sorry, I'll upload the notebooks after the session. I haven't uploaded it yet.
Okay, can later put in the chat also, because you will need one of the notebooks later for today. So for week 3 and week 4, I'm still in the middle of crafting it out. Okay, but I'll send it as soon as it's out. Okay, so this is the rough program. We'll be touching on convolutional neural networks and recurrent neural networks as the last 2 weeks. Okay, so what to expect for this thing? Okay, so I actually not quite keen to go through like the math proofs behind everything. Okay, I would like to go for more practical approaches. Okay, want to go through like how exactly, what are the intuitions behind this algorithm or these methods. Okay, there will be some math. Okay, but if you do not understand that, do not worry. Okay, the math will basically be just differentiation. Most of the math needed, okay, because of the algorithm called backpropagation, which I will cover on later. Okay, so yeah, feel free to ask questions anytime during the presentation. Okay, and yeah, the format for each week will be, I will go through a little bit of the theory. Then after that, we get hands-on and do the practical. Okay, if anything in the deep learning world is that just knowing the theory itself is not going to do you any good. You have to code it out yourself. Okay, if not, you wouldn't be able to understand exactly what's going on. Okay, but that's it. There's a lot of models that even I cannot code because they are just too big. So you have to exercise discretion here. But for this, at least for this 4 weeks, it's definitely runnable within 5 minutes, those kind of models. So yeah, feel free to try it out. Okay, so before I touch on the main thing proper, I would like to give you some motivation of why we are touching on neural networks. In the past few weeks, you've been doing more of like the traditional machine learning methods, SVMs, random forests, I believe, linear regression. So like all these actually work pretty well. I mean, especially SVMs. SVMs with a different kernel can approximate like a lot of different functions with the right kernel function. Did you all cover on the kernel function?
I didn't do SVMs. I did random forest, linear regression, logistic regression.
Okay, yeah. So SVMs is a kind of also a kind of classifier. Okay, and one thing about neural networks is that neural networks can actually rival the performance of all the above mentioned methods. Okay, so you might ask like, why learn it? Okay, let me just show you like some of the more relevant things right now. So what can machine learning, deep learning do? So like on the left here is an object detection that I personally did on a Singapore road using ResNet ReceptionNet from Google. It's the TensorFlow hub. So it's quite cool, right? I mean, you can actually detect all the cars quite nicely. Okay, and the motorcycle. If you want, you can detect people as well. So just by training the model on ImageNet, which is a very large image data set, and it can already detect quite accurately where are all the different objects in the scene. So imagine if you have a robot moving, you want to let it know what is there, what are the objects. In fact, people are working on even depth perception and everything. In metaverse, you will need quite a lot of this kind of applications in order to fuse with your reality. Okay, like if you want to go out of bounds, or like what is the area of space you can walk before you bump into a wall, all this you can use deep learning to do it. Of course, you can also use sensors. Elon Musk is trying to do self-driving cars. Okay, mainly pure vision based without even LiDAR. But I mean, I would think that having other sensors would be equally important as well. Okay, this is just one application of it. Okay, the other one basically is this quite new, DALL-E. Have any of you heard of it? Okay, this came out just this year. So this is from OpenAI. And it is impossible for any of us to train this model because it's just too huge. But this model is quite cool in the sense that you key in a text, okay, and out comes an image that that predicts the meaning of it. Okay, Takuma, you said about GPT-3. Yes, GPT-3 is at the bottom here. So it's a transformer-based model, okay, that basically it helps you to like complete a question, if it finds the answer for you, or complete a sentence. So GPT-3 is at the bottom. You can look at it. It is actually quite semantically, structurally correct. Okay, and actually people have used GPT-3 to create fake blogs before. And that, like, even the fake blogs, people didn't even know it was fake. Talk about fake news. Yes, GPT-3 can help you do fake news as well. So, you know, it can be quite dangerous. I mean, some of the applications over here, but these are just some of the possibilities that you can actually do with enough training data in your deep learning models. Okay, so reinforcement learning. Okay, I touched on a little bit also because I'm doing it. Okay, so on the left here, you see AlphaGo. This is a 2016 match where the computer actually managed to win the top human. Okay, one of the top humans. Okay, he may not be the top, but he's one of the better ones. Okay, so this shows that, like, if we use a neural network, we can actually approximate even very complicated possibilities, like a Go bot. Okay, there's a lot of possibilities there because a Go bot can have 3 different positions, like either blank, black, or white. So there's 19 by 19 squares. So imagine 3 to the power of 19 by 19. That's the amount of state space that we have here. Okay, you minus away rotations, reflections, but it's still very, very expensive. Like, it is impossible if you were to use like a traditional lookup table, you cannot do it. Okay, but surprisingly, with neural networks, you can. Neural networks can approximate something as large as a Go bot. So that is certainly quite cool. I talk about more recent ones. Okay, this isn't exactly that recent. Okay, but OpenAI Dota 5v5. Okay, they also created something using deep learning. Okay, so these are some of the applications that we can do here. Okay, now we go back to the basics. Okay, what you have seen over here is what people have done over years of research. Okay, I mean, training these models takes months or so. So now we go back to the basics. You don't expect to code something as complicated as that because those require a lot of compute power. But now let us understand, okay, how all these accomplishments can be done. So we have to ask ourselves this question, okay? In the neural network, what exactly is a neuron? Okay, so I go back to biology, okay, because neural networks were inspired largely from biology. So, you know, in our brains, we have this thing called neurons. Okay, and each neuron basically is like this thing here. Each neuron has a cell body and an axon. Okay, so once this thing has an action potential, it spikes. The voltage gets passed through the axon, and then at the recipient neuron, there's a dendrite here. So this is called a synaptic gap. Okay, there's neurotransmitters passing through it. Okay, details you don't need to know, but basically after passing through it, this will trigger action potential and then go through the next neuron again. Okay, and if this neuron triggers an action potential, it will then trigger to the axon of the through its axon and then potentially touching another neuron. So very simply, just having like a sort of thresholding thing, like when the voltage exceeds a certain threshold, you spike and do an action potential. This mechanism of doing so and connecting neurons together in some fashion can already give rise to quite intelligent structures, okay, especially because, like, you know, if this is the structure of the neurons in the brain, of course, there's a few different kinds. Like, for example, there's like this, there's this thing called a pyramidal neuron, where basically it has a lot of dendrites. Okay, so actually there's a lot of work by Numenta trying to do this. I'm personally quite inspired by it. So trying to take inspiration from the brain, like there's a kind of neuron that has a lot of dendrites here, and basically any of these dendrites activate, okay, you can also trigger the potential. So different neurons got different structure, okay, and all these things link together. Okay, even this mechanism here is very complicated, okay, and it's not really fully modeled in the artificial neuron. Okay, but what is modeled is that if, let's say, the presynaptic neuron triggers and then shortly after you trigger the postsynaptic neuron here, okay, the more you trigger here, okay, the more you trigger, the stronger the connection. So the next time, less neurotransmitters are required in order to trigger the next neuron. So in some sense, this biological mechanism is similar to like increasing weights in artificial neural networks. Is similar, again, in a very crude sense. Okay, but the idea is, if you know, there's this Hebbian rule. Okay, they say if you fire together, you wire together. Okay, that is quite true for neurons. If the neurons fire, okay, shortly after they'll form an association and then they'll strengthen that connection. So the next time it will fire even more readily. Okay, so that's the idea. Okay, using neurons, okay, each of them following their own rule, and then they trigger, and then after that, you find a way to update the state such that you make some connections stronger, some connections weaker, and so on. Using that kind of like learning, somehow you're able to learn very complex functions, especially in like humans. Okay, you can do a lot of things just by using this kind of feedback mechanism. Okay, so enough about the biological neuron. Of course, when we do our current neural networks, I can say that we don't really model a lot of what the traditional neuron has. Okay, what we do instead, we do something even more crude. Okay, we do a very, very simple example. Okay, you're ready to see how neural networks bastardize this biological model? Okay, although I say bastardize, it is a fairly workable and very easily implemented model. And it works. You know, the main thing for engineers is it works. You know, why closely model the brain when it's so complicated when a simple one will work? So this is how computer engineers or the early AI researchers did it. Okay, so for the entire slide here, you will see this blue color stands for inputs. Okay, and then the yellow color one will stand for output, and then green color will stand for the neuron itself. So for the rest of the slide, this is the notation. So what artificial neuron does is that it takes an inputs, maybe like X, okay, multiply it by a certain weight, signifying the strength of the synaptic gap, how many neurotransmitter receivers are there in the channel. I mean, it's a sort of a proxy to it. Okay, multiplied by the weights, okay, and then you sum up all the weights. Okay, if the sum of these weights, okay, is beyond a certain threshold, okay, and this is defined by the activation function that will tell you what's the threshold to fire. Okay, if it's beyond a certain threshold and it fires, then it will fire and then it will output it in the next part. So typically, if you look at the equation, it should be something like that. Y equals to F of Wx plus B. Okay. Over here, we don't have the bias term, but there's also another term here that usually is typically modeled in the neuron called the bias. Okay. So with the weights and a certain innate bias, if it passes through a certain threshold, usually like maybe a step function, if it passes through a certain threshold, you output it. Okay, if not, we don't output anything. So this is the typical structure of a neuron. And this structure is repeated in all the other neurons that we'll see later on. Okay, let's move on. Okay, so what are the common activation functions? So as I said, the activation function is simulating like an action potential. Okay, you need to pass a certain threshold, then it sends the signal through. If not, it doesn't send a signal through. So it's something like a gate, and there are a few popular gate functions. Okay, in the beginning, people like sigmoid and tangent H. Tan-H, hyperbolic tangent, okay, which is the top two here, the equations as shown. Okay, what this is that you see it starts off gentle and then towards the center, okay, it suddenly triggers a spike and then come up here. So this is like the action potential spike if you talk about biological terms. Same for tangent H. Okay, just that tangent H, okay, actually I should say hyperbolic tangent, tan-H, okay, is from -1 to 1. Okay, the slope is a little steeper, but the shape is similar to a sigmoid. Okay, but for practical purposes, it's easier to differentiate a sigmoid than a tan-H in terms of the complexity. Okay, then more recently with Hinton, okay, the more recent activation functions are called ReLU, rectified linear units. The rectified linear units are quite different from biological neurons, okay, but they work quite well for neural networks. So you know, there's always this tension between what's biology and what's efficient. So ReLU is quite efficient. Why? Because ReLU, when you differentiate it, you only differentiate when the values are greater than 0. Okay, so when you differentiate Z, you will get 1. It's very easy to differentiate this. Yeah, so as compared to the sigmoid and tan-H, ReLU is kind of preferred nowadays because it's easy to differentiate and it leads to a very like large gradient. So this can actually help to like train the neural network faster also, okay, by my observations. Okay, and over here, if let's say the output of the neuron is less than 0, then it won't fire. So basically, ReLU will only let the neurons signal pass through if the output is positive from the summation of the Wx plus B. Okay, leaky ReLU is a kind of ReLU that has a negative part where you let it pass through a little bit with a factor A. Okay, why people use leaky ReLU? Because for leaky ReLU, it enables gradients to flow even when the output is negative. Okay, ReLU leads to a lot of dead neurons. Okay, dead neurons in the sense that they don't fire after a while because their output region is in the negative part. Okay, please let me know if I'm talking something foreign to you. Okay, I'm just trying to explain the intuition behind all these activation functions. Okay, so ReLU leads to a lot of dead neurons, and sometimes people have found out that it can be hard to train the network, okay, when a lot of the neurons are already dead. Okay, so these are the activation functions that are typically used. Okay, most common is ReLU. Okay, any questions so far before I move on? Okay, let's go on. Okay, so now we need to find out how to learn. Okay, so in the actual neuron model we saw earlier, there are a few variables that we need to learn. We need to learn what is, firstly, W. Let me go back to we need to learn what is W. Over here, the W are all different for each input. So W1, W2, W3, and so on. And you also need to learn a bias function inside this neuron. Okay, so this all needs to be learned. And how do we learn it? We have to learn it by giving it some form of an objective function or a loss function. So in this case, you have a loss function. Okay, and then from the loss function, then you give it some error signal to let the neural network correct its weights and biases, W and B. So in some sense, it is like, you know, if you were to like maybe train a dog to like train a dog to fetch a ball. So if the dog fetches the ball, you give it a cookie. If the dog doesn't fetch the ball, you spank it or something like that. So this is something like reinforcement learning, where you try to make the loss function such that the loss is high when it is undesired, when the output doesn't correspond to the expected output. When your predicted neural network output doesn't correspond to your expected output, the loss will be high. Okay, and then the neural network will then configure itself to try to make this loss low. Okay, so this is the idea of the loss function. The loss function is like a guide to tell the network how to learn. And this loss function is very important. Let me emphasize this again. The loss function is very important because it is the signal where the neural network takes to find out whether or not its predictions are good. If your loss function is a bad one, it doesn't really give the neural network the right training signal, then the neural network will have very huge chance that it will not reach the desired output that you want to. So this is the mechanism behind learning. So some of the main loss functions that we see quite a lot nowadays, okay, for regression problems. Okay, regression problems are problems like predict the house price, predict the number of, I don't know, the number of clouds in the sky or something. I mean, something that contains a number, and then this number is a continuous variable. So for regression problems, like if you learn in like even for linear regression, you use like the mean square error, you minimize the mean square error in order to get the best fit function. So similarly for neural networks, you can put the mean square error as the loss function. You minimize the prediction gap between the output prediction and the input prediction. Output prediction of the neural network and the expected answer, which is the ground truth. So you minimize this. By minimizing this, you make the network predict better and better. You can also use mean absolute error. Okay, but this generally is not used. Okay, because it's not as fast converging as the mean square error. Okay, so just one thing to highlight, okay, is that for all these regression problems, you want to typically put, if prediction equals to actual, you want the loss to be equal to 0. So this applies for all kinds of loss functions. Okay, you don't want to penalize the network at all if it's predicting perfectly. So similarly, if my y hat is my prediction and y is the actual, if they are both equal, my error here is 0. Same thing for mean absolute error. If they are equal, the loss is 0. So this, just take note, okay, this is a very important thing. When you design your own loss function, this is what you need to take note of. So there's also another kind of problems called the classification problems, where you have a few classes. For example, dog and cat. you want to classify an image to a dog or a cat. So the most common most common loss function used is called the cross entropy. Okay, basically they take the summation of a y log y hat, where y hat is the predicted output probabilities and y is the actual output probabilities. So this is known as the cross entropy term. Again, if let's say y equals to y hat, okay, this actually won't be 0, but this will be the minimum when y equals to y hat. Okay, so yeah, as long as the loss function is, yeah, I'd like to correct myself here. Okay, the loss function is not 0. The loss function is the minimal point. As long as the loss function is the minimal point when the prediction equals to actual, then that is a good loss function. Okay. We will probably understand this better when we do the coding exercises. Okay, just want to highlight some of the loss functions here. So yes, now we move on to the multi-layer perceptron. Okay, so I need some audience involvement here. All right. So we have a few functions here. So over here, we have like the x-axis and the y-axis. If you want to do a few functions, like for example, the n function, okay, anything that has basically only this white color one, when both x and y are 1, then we will output as a 1, which is in this white square here. So given that, let's say for a very simple neural network that has only like one linear boundary, like one line, okay, can you draw one single line to separate the black and white circles in this case here? Okay, sorry, the Takuma, you talking about the cross entropy, is it? Okay, how about this? I will give you more slides on this next week. Okay, when we touch on the classification problem. So you can just roughly treat this as, okay, minimizing the, okay, this is a probability distribution of your actual and your output prediction. You want to make the probability distribution as close to each other as possible. Okay, so this is the intuition behind cross entropy. Okay, because only when each of the output predictions matches, okay, this will then be minimal. Okay, so this is the rationale behind cross entropy. You want to make the prediction between the actual prediction and your predicted prediction, the probability distribution, you want to make it the same. Okay, I mean, I can touch on this more next week. I just didn't prepare the slides this week for this. Yeah, I hope that clarify. Takuma, do you understand that? You're just trying to make the prediction, the probability distribution of the outputs the same.
Yes, thank you. Better imagination now.
Okay, I'll put more slides on this next week. Okay, to basically, but you understand the mean square error and the mean absolute error?
Yeah.
Okay, thanks. All right, so just want to check. Can we separate the n with one line? Anyone can answer? Can we separate with one single line, one straight line? Can we separate the white circles and the black circles in this case? Okay, we can, right? Yeah, so just to show you, okay, you can just draw one line like that. Okay, how about this over here? The or, oops. Okay, in the interest of time, okay, I will just tell you the answers. Okay, so the or, actually you can also draw one straight line to separate the two boundary like that. So remember, neural networks have a thresholding function, right? So anywhere below this amount here, okay, it will be activated as 0. Anywhere here will be 1. Same thing for all. Anywhere here will be 0. Anywhere here will be 1. Okay, so this is the problem. With just one single line here, can you separate the black square and the white square over here? So the black circle and the white circle in this XOR diagram. Yeah, anyone? Yeah, so, okay, so I'll just give the answer. Okay, so for X, yes, thank you, Takuma. So for XOR, we are unable to separate the white squares, white circles from the black circles because a single line wouldn't cut it. Okay, like you can draw the line anywhere, you will still have a case where the white and the black circles will be in the same area where you divide the decision boundary. Okay, so this is not a good. It basically shows that there's some issue with. Okay, if let's say you want to do a curve, okay, you also can't really do a curve for this. Okay, because sometimes your activation function, you're right, you can do a curve for the action for the activation function. Okay, but if we were to look at this case here, I mean, how will you draw the curve? You have to draw the curve like that. Yeah, so currently, unless you specially handcraft an activation function, if not just by using any of the activation functions we've seen earlier, like the like the, what do you call it? Sigmoid, 10H, ReLU, you won't be able to do this kind of decision boundary like that. Okay, so there's no way we can do this. Okay, and that is why with a single layer, I'm talking about just a single layer of a neural network, which is what we have seen earlier with just like WX plus B, just a single layer. We are not able to do XOR with a single layer of neural networks. And this was why neural networks was abandoned sometime in the 1980s, because Marvin Minsky, one of the famous AI pioneers, showed that the perceptron, which is a single layer neural network, cannot do the XOR problem. Okay, so, but are we doomed? Okay, so of course the answer is no, because we are still doing neural networks now. So someone has solved this problem. Okay, how do we solve this problem? Okay, so the answer is actually very simple. It's simple in hindsight, but it took a while for people to find out back then. So if let's say you have an input directly connected to your output like that, this is a perceptron, a single layer neural network. Okay, what if we extend it such that this now becomes like the intermediate layer, and then this now is our output? Okay, so it turns out that if we were to do it in this manner, where you do a multi-layer perceptron, okay, we can do the XOR function. So I'll give you some intuition behind this. Okay, why can we do the XOR function with double layers? Okay, imagine if my first layer, okay, I have the inputs. Okay, let's say I have my input X and Y here, going to my first layer neural network like that. Okay, this is my like X1 and X2, signifying the two states that we want to do XOR on. So imagine we have one network like that. Okay, this method, this network and this network can implement a thresholding function where it can like maybe do an AND function. Okay, but my drawing is okay. Yeah, so if let's say we let this top two network do the AND function, okay, and then maybe at the back over here, we can then approximate it with the output network with also an AND function. So, you know, if we have just one single layer, we can do the AND or the OR function, right? So how does this work? So this is how you do it. You draw one line here, okay, and then you set everything here as 0. Okay, this will be my network at the top here. Okay, then if I draw another line here, okay, this will be my node over here, and I set everything over here to be 0. Okay, can you see that we have drawn two decision boundaries? One to tell you everything here is 0, okay, which is the bottom node. Okay, and one to tell you everything at the top there is 0, which is the top node. So how then can we fuse these two together into one? Okay, with just one single layer, we can't do it. Okay, we can't do it. We need a second layer. We need this layer here to take the two decision boundaries that we have already classified them to be 0. We need to, okay, actually, I think this is not an AND, this should be an OR. We need to OR them together. So in this case, if any of them are 0, so we basically add these two regions together. So this will be my 0 regions. So simply put, you cannot divide with one straight line. No problem, you divide with two straight lines. And thereby the multi-layer perceptron was formed. Yeah, I hope that kind of gave you a rough picture of how multi-layer perceptrons work. They build on the input from the first few layers so that you can use very simple functions for the next few layers. But because you have some processed inputs from the first few layers, you are actually doing very complicated processing overall. Okay, but within that layer itself is performing a very simple operation. But because you stack these operations together, you perform a difficult operation. Okay. All right. Hopefully this was something new for everyone. Okay. I mean, when I first started, this was kind of hard to see, but this is why we need more layers for the neural network, because just using a linear decision boundary or like a non-linear decision boundary is not sufficient in order to generate like this kind of very complicated decision boundaries. Okay, so now some exercise for you all to think about. Okay, why must our activation functions, okay, in the hidden layers be a non-linear activation function? Like, okay, just now you saw the activation functions at the back here. All of them are non-linear. Okay, by non-linear, I mean not a straight line. Okay, so think about it. What would happen? What would happen if I put an activation function that is a linear one, that is a straight line? What would happen? Okay, so try to do this thing here. Okay, if I have a function fx equals to x, and then this is fwg plus h. Okay, so basically what I'm doing is I'm implementing a multi-layer perceptron. Okay, I have two neurons here. Okay, the first neuron here takes in a weight. Okay, and then it has a bias of h, of b. And then the second neuron here takes in a weight here also, and it has a bias of h. Okay, so this g over here represents, when you look from the neuron's point of view, this output here is g. Okay, so if we were to use a linear activation function for the neurons, what would happen to the overall function here? Okay, sorry, the overall function is this one, f wg plus h. What would happen to this? Okay, I hope I haven't lost you. What will happen to this activation function here if I have a linear activation function even in the first node over here? Anyone?
Because it doesn't have represent threshold.
Yes.
It always gives you a spike, so it doesn't classify.
You're right. You're right. So actually, that's exactly correct. Okay, if we were to just use a linear activation function, there's no thresholding function like how you have it in the biological neuron. And the end result is that after we do the math out, you find that actually it is still okay, because this basically is the coefficient for your W, and this will be the constant term here. So what you find out is that you will still have essentially a straight line. Okay, so if you were to use linear activation functions in your hidden layers, the network will be no different than if you just don't use the hidden layers at all. Okay, this is a very important point again. Just want to give you the intuition behind why we need to use non-linear activation functions in a neural network. Okay, I hope that's great. Okay, now let's move on. Okay, so this is something interesting that I crafted out for everyone today. It is something that I don't think you will find anywhere else. Okay, I came out of this myself. So not the credit assignment problem, but the exercise later that we'll be showing you. So for the credit assignment problem, okay, I'll give you about maybe 2 to 3 minutes to think about this. Okay, so now imagine you are the boss. Okay, you've been promoted to the boss, all right? Okay, everyone's the boss now, okay? You are a boss in charge of a few different workers. Okay, each of these workers here, okay, contribute a little bit to the end product, like puzzle piece. Okay, and each worker contributes differently. At the end of the day, the product will be evaluated by a third party. Okay, and then you will be given like a profit. okay, the profit can also be negative. If no one likes the product, then it'll be negative. So if based on the profit you got, okay, how do you know how much reward, how much like salary to give each worker, okay, to basically get the product to continue to be good? Or if the product is bad, how to improve the product? You don't have to think about it in deep learning terms, okay? You just use some form of like how would you solve this credit assignment problem yourself? Okay, maybe we just pause here for about a minute, okay, and then we get some feedback for this. Okay, maybe I'll just check. You can either type in the chat or you can just verbalize it. Okay, how would you reward your different workers, okay, based on the profit you have gotten? Okay, you know how much each worker has contributed to the end product. Okay, anyone? Okay. Yeah, thanks, Takuma. Yeah, you. All right. Okay, Nakata said amount of contribution times difficulty of the task. Okay, that might be one way to do it. Okay, to find out the amount of contribution each of them made, okay, to the end product. Okay. Okay, the difficulty of the task here, we just treat it as the amount of contribution. Okay, because we just treat it like there's no features here, just the amount of work they put in. Okay, thanks for the answer. So basically, it is very similar. Okay, so because we only know like how much they like contribute in terms of like their work hours, but we don't know like how much it contribute to the like quality of the product. Okay, so we cannot like just take wholesale the amount of hours that they work. Okay, because sometimes the amount of hours that these workers work may not be indicative of how well the product will turn out to be. Some people work faster, some people work slower. So one way to do this is to model each worker's contribution by the leave one out principle. Okay, so what does this leave one out principle do? Okay, so basically we hypothetically say, okay, suppose I increase your work hours by maybe like 1 hour or 1 minute. How much difference in the profit will I get? Okay, and then if let's say I increase your work hours by 1 minute and it makes the overall product worse, and hence the profit has decreased. So what I should do, I should make you work less. Okay, because making you work more make the product worse off. So I make you work less. Okay, if let's say I decrease your work hours and the product becomes worse, okay, then I should increase the work hours. So basically, is the idea of like you just do a fine adjustment with each worker, okay, and then you see whether or not this adjustment makes the profit increase or decrease. Okay, I know in real life terms, okay, it may not be the case that like you can just hypothetically assume what will happen if something goes up or something goes down, right? Okay, but in neural networks, we can. Okay, so this whole analogy is telling you like how this is actually done in a neural network. So let me just, okay, so this will be like probably, I will spend 15 minutes on this example. Okay, and then probably the rest of the slides we'll do all next week, okay? Because I only have about 15 minutes left and I want to highlight this example here. Okay, so this is the example right now that I want to show you. So suppose that we have a linear function. Okay, we just treat a very simple linear function because I want you to see how backpropagation works. Okay, let's say we have y equals to wx plus b, and then we are given like 5 different pairs of x, y, which is given by this 2, 3, 3, 4, 4, 5, 5, 6, and 6, 7. How can we find out the right W and the right B? Okay, so actually the notebook is will be shared with you at the end of this session. Okay, initially I wanted to have a like go through together kind of thing. Oh yeah,
Okay,
you
sorry, let me cut you there off there. We don't have a local notebook. So what I have been using is Google Colab. So if whoever wants to try this out for yourself, I put the link here. I have created a Google Colab. Let me know if you can see it. I didn't specifically share it, but the folder is shared. So this should be, you should be able to run this for yourself.
Okay, so I have now changed my application. Are you able to see the Colab drive right now? Can I just check whether my Colab is being shared?
Your Colab, as it, oh yeah, it is being shared on the screen. I think for Kaichi, you don't have access to the one that I just shared because it's on
Oh no, it's okay.
on my
I have sent her a version of this already.
okay.
Okay, so now we are trying to solve the credit assignment problem here. Okay, so basically we need to find out how much to reward each worker or how much to adjust. Okay, actually the more exact term will be to adjust like maybe how many hours each worker works. Okay, in this case, the hours could be M and B. Okay, these are the variables that we need to adjust. How can we adjust these variables M and B such that we make the prediction of this Y equals MX plus B as close as possible to my actual output? So given this data, X, Y, with these tuples, 2, 3, 3, 4, 4, 5, and 6, 7, okay, we need to solve for M and B. Okay, of course, if you use linear regression, it is very easy. Okay, but what I'm showing you with neural networks is exactly the same, okay, as how you would solve a linear regression, except that you don't need to know the underlying math of mean square error. Okay, I mean, you need to use it for the loss function, but when they update the parameters, you don't really need to know all this. So let me just give you all this is the prediction. So we have the initial mx plus b, and then we predict by y hat given this equation. So m and b are initialized to be 0 at the beginning. Okay, and then how we attempt to solve this credit assignment is that whenever, okay, the loss increases, okay, when we increase the value of m and b, if we increase the value of m, okay, and the loss increases, okay, it means that probably increasing m was the bad thing to do, so we should decrease m. Same thing for b. So basically, we try to push m and b in the direction, okay, whereby the loss will be minimized. So I just run through the code here. This x and y values here are the initial tuples. W and b will be my initial weights and biases, initialized to 0. Okay, these are the number of epochs. Okay, epochs, I realize I haven't covered through this term yet, but epochs is basically the number of times I look through the entire data set. Okay, then I have a learning rate here. So this learning rate will be basically like if let's say when I increase my W, or sorry, increase my M or increase my B and the loss increases, okay, then maybe what I should do is I should actually make my M, I step a small step towards a certain direction. So like this loss, this decrement M or B is decremented by the LR. Okay, so this perturb here, perturb is basically you perturb it a slight value ahead, okay, to just see whether the loss function increases or decreases. So essentially for every epoch, we look through all the samples, okay, we look at the prediction and the loss function. Then we do a slight perturbation to see how much we need to change, like whether we increase W a little bit, whether my loss increases or decreases. I increase my B a little bit, whether my loss increases or decreases. Okay, and then if, okay, let's say when I perturb a little bit, like basically I increase the value of W a little bit and the loss decreases, it's a good sign, right? So that means what I'll do is I will make my weight step a little bit towards the forward part. Okay, let me share with you this in a diagram. Maybe it's easier to visualize like that. Okay, if this is my loss and this is my weight here. Okay, if let's say if I were to perturb it a little bit forward, and the loss is lower, okay, so what I will do is, okay, I will want to increase my W by a certain learning rate, okay, which means I will try to step closer and closer, okay, towards where this minimum point should be. So again, if let's say I'm at the other side over here, I want to step closer and closer, okay, towards where the minimum point should be. So this is the rough idea of how we are going to do this perturbation. So astute people would realize that this isn't exactly backpropagation yet. You are right. I'm just introducing this idea of increasing and decreasing the values W such that we reach the minimum here. Okay, later on, when you see the backpropagation algorithm, you will realize that it's actually a more efficient algorithm to reach this point here based on the gradients. Okay, so let's try it out. Okay, let's try out to see how this works. So you can press like Shift Enter or press play over here to run this cell. And oh, wait a minute. Is it running? Okay, so we have run the cell and you can see that they have found the equation y equals to x plus 1. So using this perturbation method, it kind of found the optimal gradient. Okay, so all right, so that's exactly what is happening with like your weights and biases in the neural network. It is a similar concept, except now I would like to introduce this thing called backpropagation. So backpropagation is basically instead, okay, so you look over here, instead of just doing W minus LR, which is what we have done in the front part, we now multiply the learning rate by the gradient here. Okay, let me erase this. We multiply the learning rate by this gradient here. Okay, why do we want to do this? Okay, this helps. Okay, so if you look at the loss function, okay, with respect to our parameter again, like that. Okay, remember, if one way to find like where to go is just like to take a small step in the location there to find out whether or not the minimum is on the left or on the right, which is what we did in the first part. Okay, but what if I told you that if we were to just take the gradient, okay, if we just were to take the gradient, okay, let's say the gradient of this point. The gradient of this point will be negative, right? And it will be very steep. Okay, it will be a high number. So if we know that this gradient here is negative, and then the learning rate is always positive. So in essence, what we are doing is we are doing W. Okay, we are basically given the initial W. We are taking a small step towards, in this case, a large step. We are taking a small step towards the minima. Can you all see here? Basically, your gradient update will make the parameter go closer and closer towards where the minimum is. And in this case, how much to step through depends on the gradient. So over here, like let's say the gradient is a little less. Okay, the stepping, the way that it step forward will be a little lesser also. So it will step forward a little bit here also. And over here, it will step even lesser and lesser until it reaches the minimum. Okay, so this is exactly what backpropagation does. It makes the parameters adjust bit by bit and bit and bit. Okay, if the slope of the curve is very steep, it adjusts more. If the slope of the curve is less steep, it's more gentle, it adjusts it lesser. So these are the equations used. The loss function is the mean square error. Okay, the prediction is here, Wx plus b. Okay, so we do a differentiation here. So this, okay, is basically the differentiation of this. You take the 2, you bring down, multiply here, you get y minus y hat. Okay, then you differentiate this part for the y hat here, you get minus 1. So this will give you this equation. And dy hat over dw, okay, is this one. Dy hat over dw is actually x. Dy hat over db is just 1 because it's a constant term. So then you can get your two gradient parameters updates here. And then after we get these two gradient parameter updates, okay, we can then sub it back here into the learning rate. Okay, I pause here for any questions. Okay, because this is a little technical right now, but this backpropagation is the crux of all deep learning methods. So I hope that it's understandable what we are trying to do here. I just pause here for maybe like a few seconds for any questions. If any of you all want to clarify any of this, how we update W and B.
Chongmin, do you have the equation, the full equation of forward and back propagation, just to compare and see what's going on?
Oh, it's here, it's here. So forward is this two.
Okay.
Then the backward is this two. I mean, the backward will be this two. Oh, you're talking about showing it in a diagram, is it?
Correct. Like having when you drew the nodes, the two layers, and then forward, what happens to numbers when you go forward, and then when you reach the end, how the model compares the actual result to the prediction result, and then the difference goes backwards. Like how does it go back?
Oh yes, actually I do have a slide on that. Yeah, maybe I will talk about that slide next week. Okay, because sorry.
Doing it this way is hard to imagine for.
Understand.
Yeah.
Okay, so maybe okay, you see over here. Maybe I just draw the notes here. Okay, let me just erase this. So just to let everyone, so let's say this is my X, my input. I go into a neural network. I just draw the notes here. Okay, it's a very simple one note thing. Okay, and then I basically take my weight over here, and then I output over here y hat. So in this case, you can see that y hat equals to wx plus b. Okay, can you see this is like this is my y hat here. Okay, so at this point over here, what I do is I'll take my y hat. I'll take this y hat here, and then I'll do a mean square error. Yeah, so after I do my mean square error here, I will then back propagate this mean square error backwards. First to y hat. Then after that, I'll back propagate to w. And I also back propagate, there's also a bias term in here, right? I also back propagate this term to b. So in essence, the forward propagation goes from left to right, but the back propagation goes from right to left. Okay, I hope this is clear. Yeah, is that okay?
Yes, if there's any questions, we were happy to take questions. Do you have more time? Otherwise,
I do have more time. I just thought that you might need to end the session on time. I can stay.
Usually we end at 9. But if you have to go for your own commitments, yes, please let us know.
No, that's fine. It's fine. Don't worry.
Okay. So I would like to add that this is foundational knowledge. It's quite important that you understand this because in the future it's going to get a bit more complicated, and if it's too difficult to understand now, please tell us if you don't understand. Like if it's okay if you totally don't understand anything that's happened, we will try to explain it again. But the magic of deep learning is this, because whatever you can do with the traditional models, deep learning does it in every node. So in this diagram, this is a typical traditional one pass of a traditional deep learning algorithm, but one pass of a traditional machine learning algorithm. Deep learning does this one pass for every single node and then does backpropagation. So that's the power of deep learning.
Okay, so actually, I would like to just run the cell here. Okay, you can just see. So this cell over here is exactly the same as what we saw earlier. It's just that now we don't really need the loss and we don't need the perturbation. Okay, why? Because this perturbation part, where we perturb a little more or a little less, to find out how much the contribution is, we don't have to do it anymore because we have the gradients now. The gradients do that function for us. So now we just multiply the learning rate with the gradient. And this thing here is exactly what we have over here. Y minus y hat times x. Oh, I realized there's a typo here. So this is actually y minus y hat minus 1 times x. Okay. Yeah. Okay, this should be actually y1. Yeah, I think just now when I did the equation, okay, it should be like that. Y minus y hat x. Okay, so please take note, this is the actual equation up here. Okay, so when we work y hat, oh, actually it should be y hat minus y. Yeah. Okay, so these are the two equations that we take. Okay, and this will be multiplied over here for W and for B. Okay, so let's run this cell, and you realize that, okay, oh, the learning rate should be like maybe 0.01, a little more. So you see, it worked. So you can see that deep learning methods like this is actually quite sensitive to like learning rates. Okay, if my learning rate is very high or if my learning rate is very low, it may not converge to the right value. So there's a whole science or whole art of trying to do learning rates. Usually people start from like 0.1 and 0.01, 0.0001. You keep going down exponentially, and then you find the right learning rate before you fine tune further. Okay, so this is an example. So whatever you see in this cell over here, okay, so I'll upload this new notebook again later. I'll pass it to you because of this equation here is wrong. Okay, so what you can see over here is that the gradient descent algorithm, again, manages to learn just by local gradients itself. It manages to learn the right loss function. And then this will be, the final equation is correct. So if you extrapolate it to many weights and many bias terms, you will realize that this is exactly what we see in modern day deep learning networks, where just from the loss function itself, you can backpropagate and update all the parameters backwards. Okay, so I hope this is an illustration of how this is done. Okay, and what you see, this code over here, okay, a version of this is actually implemented in TensorFlow as well. Okay, so like when you do TensorFlow, this is exactly what's going on behind the hoods. Oh yeah, thanks, Dr. Yeah, this is what's going on behind under the hood. And just for completeness, okay, I also included some code here for TensorFlow for the linear regression. So we use like a TensorFlow variable here. And first we import TensorFlow as TF. So
sorry, John, could you explain what TensorFlow is?
Oh, okay. Yeah, TensorFlow is a auto differentiation framework. Okay, I realized something. Maybe I should have gone through the slides first because I do have slides on all this, but I decided to go through this notebook first. So yeah, next time I'll go through the slides first. Yeah, thanks for pointing out. So TensorFlow is an automatic differentiation framework where it allows you, all these complicated equations here. Okay, you don't really need to do all this in TensorFlow. Okay, because TensorFlow can do it automatically. You see, that's the cool thing. You supply TensorFlow with these two equations, and TensorFlow calculates all this automatically for you. And there are many times where researchers have calculated the wrong gradients in the past because they had to do something like this. Like you see, just now I made a mistake typing here. Yeah, so stuff like this is very common. But if you use like auto differentiation, you just give it the forward values like this one and this one, and you put it under a gradient tape. Okay, gradient tape will record the gradients. Okay, then you find out what the gradient tape recorded, and then you then proceed to do your update of your variables here. You can see, okay, let's just run this. So you can see that if we use TensorFlow to run this, okay, you can see that it's a little slower, okay, because TensorFlow needs time to initialize the nodes and everything. You can see that we can also get the same equation in TensorFlow. All right. So from next week onwards, okay, we will be going through more of the code using TensorFlow. But the code over here that you see right now, this is really the bare bones structure of like what is going on in the basic TensorFlow. Because next week onwards, we will be using this architecture called Keras. Keras has a lot of abstractions so that you don't have to use stuff like gradient tape. You can actually use a lot of pre-built models that people have already done. So you don't have to do all this manual labor yourself. Okay, but why did I give this code to you? Okay, it's because I want you to understand that under the hood of all these frameworks that you see right now is still backpropagation. And the backpropagation is exactly the same as what we covered up here. It's exactly this. Okay, it's just that TensorFlow helps you to do automatic differentiation so that you don't have to calculate your differential equations yourself. Okay, is that clear so far? Okay, so actually that's all I have to share for the notebook. Don't know whether I still have time to cover the remainder of the slides. If not, I will go through them next week.
How many more slides do you have?
About 10 more.
Oh, 10 more. Maybe we'll pause here for this week, and then is it linked to what you're going to what you just taught today? Like, is it very
yeah, it's linked. Actually, if you all don't mind, I just spend about 5 more minutes to cover the stuff that's linked.
Okay, sure. Okay, go ahead.
Okay. Yeah, so this is the whatever we talked about just now, okay, is essentially gradient descent. So gradient descent is using backpropagation. Okay, you start from like the top of this hill, and then you take very, very small steps through the gradient, and then hopefully you find that the local minima, which is the place where the loss function is minimized. So this is exactly what I was talking about just now, the weight minus learning rate times the gradient. Okay, so you start from here and you go step by step. So if your learning rate is too small, you take very long to converge. But if your learning rate is too high, you keep bouncing and bouncing and bouncing and bouncing. You may not be, okay, actually, if your learning rate is too high, you might just keep bouncing left and right, but you will never go inside here. In fact, if your learning rate is even higher, you might even bounce out of this minima here. So learning rate is very important for the learning of the neural network models, because too large or too small will hinder the going towards this minima point here. So what we need to take note of for the loss function is that the loss function should be as far as possible a smooth one. Okay, hopefully it's convex. Convex is like a bowl shape. Okay, so that we can find a global minimum. Okay, for many years, people thought that, okay, maybe finding a local minimum, you must find global minimums. That's why neural networks didn't really take off, because you can't provably show that you can go to a global minimum. But people have found that actually local minima might be actually good enough for most cases. So because if you do gradient descent, you take small steps, you might end up at a local minima instead of the global minima. Okay, so this is the rough idea of gradient descent. Okay, so I wanted to actually step through the equations here, but I already showed you all in the notebook just now. Okay, so the forward pass goes from input to output, and then the error signals go backwards. And TensorFlow and PyTorch can do all this automatically for you. Okay, so that is the cool stuff about it. Yeah, so actually the last few parts, do I still have time? Okay,
Yes.
Sorry?
Yes, sure. A few minutes more.
Yeah, if not, actually the last few parts are very simple. So you can actually, when you do your TensorFlow neural network training, you split your data into train and test. Okay, so that you train only on the training set, and then you test on the test set which is not seen by the model. So this is how you learn that the model is not overfitting to your training data. Okay. I will touch more on this next week. Okay. This train test split, because this is very important for practical ML engineering.
We did a train test split when we were doing data engineering. So is this inbuilt in TensorFlow, or do we
you can use
do it
other tools
first?
to do it, like scikit-learn train test split.
Yeah, that's right.
Yeah.
So
So
we did it already as part of the data cleaning and data engineering. So we should do it before we input the data into the model to train, right? Okay.
So whatever you did before for other ML models, you do the same for deep learning. Okay. So okay, this batch epoch iteration, I think I'll cover all this. I'll cover all this next week, because this one will take a while. I'll just maybe touch on the last part, okay, to just pick your interest in the types of neural networks that are available. So what we've seen today is the multi-layer perceptron, okay, where you use multiple layers in order to map a more complicated function. Week 3, we will touch on convolutional neural networks, whereby we have this thing called filters. These filters are a 3x3 patch, that kind of thing, that can help you to find out, like, okay, is this part a cat, is this part a dog, or is this part around an edge, or is this part a line? So stuff like this. This is in convolutional neural networks. Okay, this one will have one whole week for itself. So this is just to pick your interest how this works. Then week 4, we'll do recurrent neural networks, where we have just like, it's similar to a MLP, just that instead of having only one way like that, your hidden state actually can backpropagate. Sorry, can actually go loop through in time. So like the state, your previous state actually is an input for your next state. So this is recurrent neural networks, used mainly for like text generation or like music generation. And then like the more advanced models, which we won't be covering in these 4 weeks, okay, something like transformers. Okay, this one is actually quite revolutionary. A lot of applications are using this right now. It pays different attention to different input values and then uses it to do some processing. So just to let you all know what's in this world. Okay, that's all for today.
There's a question from Jeremy. So he's asking whether you would cover how does a neural network train on live data, means retrain itself on live data. Will you be touching on it as an extension of convolutional?
Okay, firstly, what do you mean by live data? You mean online training, is it? You learn as you see the examples, right? As you see new examples and update the train model. Is that correct?
Yes, he said yes. Yep.
Yes, actually, I did not intend to cover that part, but that part is very, very simple. Because in a neural network, what you really need to do is to just take the train model and then you just run a few more epochs on the new data. So I mean, if you want to know this, I can put some pictures on those diagram. I mean, I can cover that. Yeah, it is actually not difficult for neural network to learn on new data, because you just need to really update the model parameters. Yeah. So yeah, that's actually an important thing, because sometimes the neural network takes months to train, and then you have some new data that you have from the last week or so. How do you update this model? You can just use the old model weights and train with the new data. Okay, so I'll put a slide on that.
Okay, thank you very much for the first lesson. If there's any more questions, we have a Slack channel. So maybe I can take your email address for the newcomers. Chongmin, do you have a Slack? Do you have Slack? Do you use Slack?
I use Slack, but I don't check it regularly.
Okay, that's fine. We'll just add you, and then if there's any questions, I can answer. If not, I'll ask you during the lessons.
Okay, sure. Now, I actually would like to go more in depth, but I would say that in a short 1 hour, that's about what we can cover. Okay, ideally, the whole back propagation can take actually 2 to 3 hours to cover. Okay, if you want to go in depth. So I hope it hasn't been too rushed. Okay, I try to make my examples as easy as possible. And yeah, I can link you all to some of the resources for more math if you are the math kind. Yeah, the course that I actually would recommend if you really want to know the full rigor is actually this deeplearning.ai. There's this professor called Andrew Ng, who actually goes through quite detailed how all the math and how the vectorization operations work, okay, which I left out for today, okay, because I want to just focus on the key concepts behind backpropagation. So yeah, for more of this math rigor, I will pass the links to you all. Okay.
Okay, thank you very much. And finally, I would like to say that his slides plus the collab notebook is uploaded to our drive. So if I think Chomi, I've shared that drive with you already. Please let me know if it's not, and then your friend as well, if she would like to have access to that. There's also material from the past 15 weeks that I did. So you can have a look at that as well. Okay, if not, thank you very much for attending, and I'll see you next week. Still at the same time, 7:45, and then we'll see how long we can go for next week.
Yeah, sure.
Okay, thank you very much. See you guys next week.
All right, bye everyone.
Thank you.
Thank you very much.
Thank you.
Thank you.
Thank you.